All right. When I first introduced you to this notation of an integral, you guys thought antiderivative, okay? And then when we put numbers in this integral, it's because we knew we were going to take the antiderivative, plug in our ending time, and subtract our starting time to find a displacement. But we know that this actually means something else in relation to f. When we first introduced the integral with these values, it's because we were taking an integral of velocity. We said, okay, area under velocity gave me displacement, okay, because that's velocity times all of my times. Okay, well, sometimes when we have an integral, we won't take the antiderivative. Sometimes when we have an integral, we're just going to think area. I say area under f of x, but I really mean area between f of x from a to b. And what's really important, and we'll talk about it in this first page of notes, is this a and b, the order matters. Okay? When I'm above the x-axis from a to b, I say the area was positive. When I'm below the x-axis from a to b, I said the area was negative. We didn't really talk about y much. We just said, hey, go with it for now. So let's talk about the y. Okay? So y. Well, let's think about areas as like rectangles, as bases and heights, widths and heights. Okay? So if my heights are up, I say my heights are positive. We're going up above the x-axis to positive y values. I say my heights are positive. Now the widths, I'm traveling from A to B. I'm going to the right. That's why I'd say my widths are positive. That's why I say my area is positive. Now here, why is my area negative? Well, it's because my heights are negative. My function values are going down to these negative y's. That's why I say my heights are negative, but my widths are still positive. Positive times a negative gives me a negative. Watch what happens if I went in opposite order from B to A. Well, we assume that things above the x-axis, the areas are positive. But no, that's not the case here. This area is negative. Now notice why it's negative. It's because this is from B to A. Order matters. It's because the heights are still positive, but since I'm going from right to left, my widths are going in a negative direction. So if I'm thinking of areas as like heights times widths, positives times negatives, that's why my area is negative. Which means below the x-axis, I'd consider this from B to A to be positive. The heights are negative, but the widths are also negative. The area is positive. What that means is, if you're going from right to left, your area is the opposite as it is from left to right. Whenever you're asked to find an integral, an area from like 4 to 1, if this is 4 to 1, I would say, you know what? Just find it from 1 to 4, but then take the opposite of your answer. Does that make sense? Okay. Last little one that we need to know about before we tackle the main part of this lesson is if I go from A to A. What do you think? Discuss with your neighbors. What if I have an integral from A to A? What do you think, Mr. Butcher? What was your first instinct? 0 is correct. Why? The height could be positive or negative. Who cares? The width is 0. I'm going from A to A, from 1 to 1, from 3 to 3. I have no width. So you'd think it's like a line, it's a constant, but it's like, no, I have 0 width. So that's why it's 0. Okay? Okay. Well, we're going to be talking about and analyzing a thing called an accumulation function. An accumulation function is this. It is an integral with a variable inside of it. And the variable's in the boundary. Okay? Now, this is read the accumulated area from 2 to x under F. Notice variables are not the same. This is important. The variables can't agree. And what we will typically have is this other function g. Now, we've used g a couple times in the past, like with inverse functions. We used it when we first introduced like the chain rule and stuff like that. Like, don't think that they're related. This is a different g. I'm just saying here's a different function other than f that is equal to the accumulated area under f. Okay? So don't think about inverse derivatives or anything like that. This is just a different g. Okay? All right. And notice g has x in it. First thing we're going to do is just evaluate values of g. So g of 4. All right, well, that 4 is replacing x. Okay, that's x right there. It's not replacing t, it's replacing x. So I will plug in 4 just where x is. I will not replace t with anything. It stays as f of t dt. Now, you don't have a calculator. In the past, if you were given an integral, you would think, oh, I would have to take the antiderivative. Nope. You can also think of an integral as being the area. Now let's look at over here. What are you given? F. Now it's f on an x-axis, and you might be like, well, I have f of t, so this can't be the same. Well, it could be f on a t-axis. It doesn't matter. The variable doesn't matter. They just can't agree. Okay? Just like how when you were evaluating integrals, even though of velocity, you had t's in your velocity equations, you typed it into your calculator with x's, you got the same answer, right? So don't worry about that. This is an integral from 2 to 4 of f. Well, can you answer this question? What is the answer? Discuss with your neighbors. Four is correct, because you know that, yeah, I could take the antiderivative, plug in 4 and plug in 2, but you know this is also area under f from 2 to 4, and you actually have an area that you can find. It's not a curve. You can use geometry. You can find the area of that shape. That's just a square, width and height of 2, that's 4. Okay, now let's look at g of 7. Okay, so it's going to be 2 to 7 of f of t dt. That means I need this area from 2, include this area to 5. Now here's what's important. Some of us are thinking under, and they might be thinking, oh, this area too here. But that would be incorrect. It's the area between the x-axis and your function. So that'd be that area too. Okay? So we'd need to add up all those areas together, and we'd be able to answer this question. So we already know this is 4. This is a triangle, 1/2 a base length of 1, a height of 2. So this is just 1. This is a triangle, 1/2 a base length of 2, a height of -2. This is -2. So I got 4 plus 1 minus 2. That's it. That's my answer, 3. Okay, do the last two, please. Please check your answers with the neighbor. Okay, 2 to 2, I have no width. My area is 0. 2 to 0, my advice. 2 to 0, order matters. Go ahead and just say, you know what? I'm just going to take the opposite of my integral from 0 to 2. I'm going to find my area from 0 to 2 and take the opposite of it. This is a trapezoid. We will talk about how you have a formula for this trapezoidal area in the future. For right now, it's easy enough to do rectangles in a triangle. You get that that's 3. So the answer would be -3. Okay? Cool. Most of our problems, we are going to just be given a graph of F, and we'll be asked questions about G. Okay? It'll be Unit 3 type questions. Shh. Turn around, Miss Corey. Unit 3 type questions. Maxes and mins, points of inflection, stuff like that. But of G, given the graph of F, and G is equal to the accumulator area under F. Okay? But to understand the analysis of G, and the analysis of this integral, we're going to do a little bit more investigation of this. And instead of just F, I'm going to give it a function. Like, let's say we have the accumulated area under cosine. I could actually find an expression for G of this by taking an antiderivative. We'll go back to, when we were first introduced with integrals, we said take the antiderivative. Okay, so I take the antiderivative of cosine, I get positive sine. And we talked about how, we remember with these numbers, it's like find the end position minus the starting position to find your displacement. We use this line to denote, don't forget to plug in X, don't forget to plug in, or B, don't forget to plug in A. And reminder, since we're subtracting, the C will cancel, so I don't need it. I plug in, all right, X now. This is different than what I'm used to. I'm used to plugging in values, but I'm going to have sine of X. And then I'm going to subtract pi over 6 plugged in, a sine of pi over 6. That ends up being a half. The reason why we do this is because we're going to take the derivative of this accumulation function. Okay? We're going to take the derivative of this. Now, instinctually, you guys will be able to tell me what this equals. What is the derivative of that integral? Go ahead and chat it up with your neighbor a little bit. What do you think? If you take a derivative of an integral, what do you think you get? What we should be thinking is like, okay, integral, antiderivative. Derivative of an antiderivative. Just like, don't they just cancel each other out? And don't I just have, like, whatever is inside? So let's see. I'm going to take the derivative of this that I already evaluated. This ended up being sine x minus a half, right? We did this in the previous example. If I take the derivative of sine x minus a half, do I get cos t? No, what do I get? I get cos x. The derivative of sine x is cos x. What's the derivative of 1/2? 0. Okay, so it's not f of t, it's f of x. All right, well, your instincts are still pretty much correct. But all that happened is I took this x, and since I'm taking the derivative, that x ended up replacing t. What happened to this pi over 6? And like, what's going on with this a? Hold on. If I changed this from pi over 6 to pi over 3, would my derivative change? No, because what it ended up being is sine x minus root 3 over 2. It's just our antiderivative with a number plugged in, which is a number. The derivative of the number 0. So please write down that this a doesn't matter when we're taking the derivative. It does when we're finding values. And then go to lunch.